Well, thank you. I came to Bacchus last night, and it was really interesting. I ran across 3 individuals from another foundry. I'm with GlobalFoundries now, so but sometimes I like to get together with people from other foundries. So we got to talking, and one was from the wafer part of the business, and one was the mask part of the business, and one was the OPC group. And they, I had a beer with them, and so they said, we have a problem, and we don't know. I think it's OPC. And they go, no, it's not OPC. You guys always blame us. It's the mask. And the mask guy says, we just do what you tell us. And so they were all playing to one another. So it got me to thinking before I gave my talk today, when mask hotspots happen, are they really well defined? The answer is no. You can have mask hotspots that impact you in very subtle ways. It's not just yield failures. And so I'd like to talk about mask hotspots and a way to potentially mitigate those with a relatively low-cost method. So you're all here at Bacchus, and you're at a mask conference, so you know mass CDU better than I do, and you know MEEF. And if you look at the roadmap, and this is a generalization, but the CDU requirements in the roadmap say 0.5, 0.9 roughly, and MEEF is 0.4 to 8. But if you get together with people, they say, MEEF is actually going to be higher than that. But if you take these numbers, you say, well, maybe 1 nanometer CDU is okay if we just do what we're doing right now. Well, I don't think things are necessarily okay. And I'll tell you why. Let's open a discussion. So MEEF typically assumes a globally uniform isotropic variability error. So you expand or dilate an OPC feature to calculate the MEEF by looking at the litho error. This is optimistic, and moving forward is probably going to be increasingly wrong. It's because these small mask features have a poor mask process margin and inherently higher variability than the mask process control structures. So this is a hotspot. Effectively, and I underscore effectively because this is not the proper usage of MEEF, but effectively MEEF may be larger for these critical structures, at least in a relative sense. So you've seen this type of plot before, but what it indicates is that the electron deposition into the energy deposition into the resist will be blurred out for small features greater than larger features. Aki just mentioned that. So, of course, line ends will be rounded and pulled back. But if you look at just the shape, you're missing a key thing. You have an inherently high probability or propensity for edge placement error here, edge error. And the reason is simply shown here. If you have a shallow dose slope and you have any source of dose error, you're going to have a significant edge error. Now, one of my colleagues at Global, who knows far more about masks than myself, he said, I've never met a mask error that couldn't be modeled as a dose variation. So what he meant there is that even for unattributable mask errors, quite often dose is a good way to model that. So if I were to first of all, which mask errors matter? This speaks to context. Just because a mask pattern has a poor dose slope, poor dose margin, doesn't mean it will impact the wafer. In terms of the main feature, you probably all know that relatively large SRF errors, for the most part, won't impact the main feature. And I'll underscore most contexts. I won't say all the time. So the image off to the left shows a simulation of a pattern I created. Actually, I generated a large matrix of patterns, and I looked at the dose slope of the main feature and the SRAF. Here I'm actually looking at the dose slope, and we're mapping the slope to the color. So red is associated with the 1 nanometer per 1% dose error. It's not shown here, but if we had half nanometers, I'll show you later, it'd be green. So this is a mask that will have inherently high variability. Now, if you want to really determine whether a feature will impact the main, or an SRAF will impact the main feature, you need to do a variation analysis. So like I said, I do very large arrays of structures, and I do variation analysis over those features, and I do statistical analysis to say where really is the real practical window. So for the most part, fortunately, everything above the design rule limit here is pretty fine. If you want to go down a little bit below, you're heading for a cliff. So ultimately, you need to use simulation. Fortunately, simulation is advanced to the point where it's really very fast and it's very accurate, and that's what I'll show you. So which patterns induce the greatest variability? So this is my OPC colleagues who know much more about OPC than myself refer to this as a offset dual aggressor, such as you see in metal. So here you have very poor dose margin for these red regions once again. When we think about it in a lithographic context, you may also wonder, well, if these are varying a lot, how does that interact with a High-MEEF feature? So many corners in a High-MEEF region probably is going to have even higher variability than fewer corners. Now, how does it correlate with silicon? If you were to take a real SEM of this mask and you do a Zeiss-Ames aerial image simulation, or measurement, I should say, you get an aerial image that looks like this. But I said, let's take the original design image, original OPC image, I should say, and we simulate that, and I take the simulated results and feed it in directly through a dual simulation methodology to calculate the wafer response. You get basically the same thing. The colors aren't exactly the same because, quite frankly, I needed to hand change the contour levels. So, but they are very similar. No, so accuracy, once again, this just simply shows that if I superimpose the contours of dose slope or dose margin, you get very good correspondence. So you can see where the mask is going to be varying a lot. That's fine and dandy. We can find those things, but what if we find those things? Is there anything we can do with it, or are we at the mercy of the mask shop? Well, I'm questioning whether we can provide some additional information to the mask shop. And we do so much analysis in an OPC flow. There's a tremendous amount of information and knowledge that we can pass forward to enable the mask to be written perhaps better. In this particular case, these features right here, when we do a an aerial image analysis, this is associated with a MEEF of 4.7, quite high. So given our knowledge of the dose slope, it makes you wonder, well, what happens if we improve that dose slope? And so what we did here is, and I'll show this in a blow-up next slide, but if we add small shots to increase that dose slope by adding dose, and we do it very judiciously, only where you really need it, we can increase that dose slope significantly. So it went from a 1 nanometer per percent dose error to a 0.5 nanometer per percent dose error. So that's a lot. So there's a lot of advantages. So there's many different dose modulation methods you can use. There's some advantage to using these overlapping shots, as you can see. First of all, they're very easy and quick to add. If you're applying them locally, as I'm showing, overhead is very small. From the standpoint of the physics, we're not adding significant backscattering. We're not adding a lot of additional thermal energy that can heat up the wafer and impact the exposure of other surrounding features, and we're not going to be contaminating our chamber. Minimal impact on write time. So it looks pretty elegant to me. And the fact is, we can get an equivalent MEEF of 3. That's pretty good. So just really quickly, this is an aerial image that results when we take the 2 masks, the conventional case, and we take the dose modulated case where we just add some additional energy where you really need it to improve that dose slope. So as we change in this case, we're reducing the VSB write energy, and we're looking at the aerial image. So you get a much greater rate of change in the aerial image for the conventional versus the dose enhanced. So this is, of course, an inherently problematic feature. Very low contrast, very high MEEF, but this is one of the realities of our business. You know, we have these kind of patterns, and but you can mitigate that effectively. Now, we were showing aerial image. What we really want to look at is the results of a calibrated simulator that takes it all the way through development and etch. So, fortunately, we can take the smooth mask shape, the accurate mask shape, feed it into a calibrated simulator, and we can then do conventional exposure, plus minus energy, plus minus defocus to determine PV band. So it turns out, for this particular case, and I can't recall which mask exposure dose I was looking at here, but you do see a significant improvement in the PV band. So what's the low-hanging fruit, you may ask? So if we can easily detect, or I should say straightforwardly, because nothing's easy in business, I think, we can straightforwardly detect high MEEF regions in a layout. And within that set of high MEEF regions, we can detect the poor dose margin features. We can simply mark those for dose modulation by any means. So if we pass that forward to the mask shop, my presumption is that we can write a mask without too much additional overhead burden by using a model-based mask data prep or alternative dose modulation method, and get some additional process window. I believe that, when I finished my discussion with my friends from the other foundry, I broke up a bit of an argument here, and they all agreed, we need to have better integration. We need to have better mask modeling. We need to be able to integrate that with our lithography simulation. And then, rather than arguing, we can get to the real data because we can simulate it.